So then shall I start?
Yeah, you can start.
Okay. Okay, thank you, Sangeeta, for the kind introduction. And I also like to thank the organizer for inviting me in this very interesting conference on the workshop that is going on. And I have already looked at a couple of lectures, and hopefully I'll go through more. Everything is available in the YouTube. And so right now I'm at IIT Kharagpur, so attending some conference on statistical physics. Okay, so now with this, let me start. So today what I'm planning to do is that an introduction to quantum thermodynamics, and this is the outline. Okay, so what I'll do, like, first I'll give a brief introduction, then an historical background that why this field has become so interesting in recent times. And then we'll try to understand a theoretical framework, very preliminary, and the key concepts in analogy to the more familiar classical thermodynamics. Because there are various approaches to do quantum thermodynamics, but we'll take the most simplest one, which is in closed analogy with the classical thermodynamics that we are familiar with. Now, these lectures I have already given, last year in ICTS, that you may look up. But today, I mean, probably I cannot cover all of them, but doesn't matter. I mean, whenever the time is over, just let me know. Okay, so I have put it in red color. So this part we have recently write a introductory review on the on our favorite teacher and professor S.P. Bhattacharya on his 70th birthday, and this is in this article. You can get it. So with this, so let me start. So by quantum thermodynamics, in what we understand naively is the following, that once we say quantum thermodynamics, it seems like, okay, it should go beyond traditional thermodynamics and incorporate effects imposed by the laws of quantum mechanics, right? Now, when I say it goes beyond traditional thermodynamics, so we first understand what is the basics of the traditional thermodynamics. Now, if we recall, then you definitely recall that the thermodynamics, the classical thermodynamics, actually invented in the 18th century to understand the basic principle or the operational principle of the steam engines, right? And the steam engine is actually a huge object, okay, with lots of nuts and bolts. Now, if you want to study or the operational principle of such steam engines with the mechanical equation of motion, then it's extremely complicated. So what thermodynamics does, it takes a very different, viewpoint. It says, okay, so let's allow the system to run and attains its steady state, then look at its average values. Okay, and then we ask about, okay, so how much work I can get with how much heat input, and then we talk about that the efficiency of these machines and so on. So this is how this thermodynamics works. And we consider, you remember that we consider very idealized cycles. For example, the most famous, the Carnot cycles. And then we say, okay, so what about the universal bound? Okay, how much work that I can extract from such devices. So in the same analogy, if we have quantum thermodynamics, quote unquote, sub-subject, then definitely we expect that quantum thermodynamics should in principle rely on some similarly idealized processes that should in principle describe a broad spectrum of complex quantum systems. Now, why is it important? Because nowadays with this quantum technology, we have smaller and smaller quantum devices. Okay, so now to simulate such quantum devices, many body quantum systems, is extremely complicated. So you can take a different, perspective, take the advantage of thermodynamics, and then study the basic operational principles of such devices. As an example, I'll illustrate that, say, for example, a laser. We know that laser is a quantum devices. The way we study lasers, we know that it requires population inversion. The question is now, can we understand laser operations from a thermodynamic point of view? Okay, so this is the philosophy or the viewpoint that we will take. Okay, now once I say that quantum thermodynamics, also the questions that comes to our mind is that whether these two disciplines at all talk to each other, because apparently these are two separate subjects, right? So the natural question we need to understand before we proceed, that is there any connections between quantum mechanics and thermodynamics? Okay, again, go back to the early development of quantum mechanics. For example, Planck's black body radiations, Einstein's photon concept, particularly spontaneous emission. So if you recall the way they are derived, okay, so in this development, early development, thermodynamics played a very fundamental role, right, in this development of early phase of quantum mechanics. And there is a very nice article by M.J. Klein in Physics Today from 1966. You may look up. The title of this paper is Thermodynamics and Quanta in Planck's Work. So which summarizes, okay, most of the early developments of this quantum mechanics, early phases. And also the third law, if you recall that, then quantum mechanics also helps to understand, okay, so in order to proper understanding of the third law of thermodynamics, you need quantum mechanical insights. So in that way, we see there is a deep connections, and why this is really required. I mean, why thermodynamics guided the initial development. You can understand that when this new mechanics appeared out of this classical mechanics, because there is some observation, experimental observations, particularly these black body radiations, photoelectric effect, which cannot be understood, properly explained from our knowledge of the classical mechanics. So you need a new mechanics. Okay, now whenever you have a new theory, you have to test whether this new theory is correct or not. Okay, because classical mechanics is now unquestionable in some sense, right? So you need to test the new theory, and the reference is the thermodynamics, whether it is consistent with the thermodynamics or not. So therefore, as correctly pointed out by Einstein, that it was the only physical theory of universal content, which I am convinced will never be overthrown within the framework of applicability of its basic principles. Now we have to understand what is the basic principles of the thermodynamics. Okay, so that is what we would like to focus on. So we have to understand what is the basic principle of the classical thermodynamics. Only then we can, translate the same language to quantum domain. Okay. Although I said that initial phases, as you can understand, there is a deep connections between quantum mechanics and thermodynamics. It goes parallel, but in the latter part of this last century, so these two disciplines almost developed separately, with one exception. I would say that this paper, okay, from 1959 from Bell Lab by Scoville and Schulz-Dubois, the title of this paper, as I mentioned, this 3-level measures as heat engine. So this paper, why this paper is important? Because this paper is considered to be the first known example of quantum heat engine. Okay, so let us understand that. Okay, so here is the basic model of this original paper. So it's from the early Physical Review Letters, volume 2. So what they consider, that in order to get this measure or the laser amplifications, you need at least 3 levels and the population inversion. Okay, so and how this population inversion is obtained? What you do in real situations, you have this, let's say you have the 3 levels, and then you use a pump, okay, to pull the population from level 1 to level 3. And what does this pump does? From the thermodynamic point of view, the pump pulls the population from level 1 to level 3 such that there is a population inversion between level 2 and level 1. So this is the pump, which acts as a hot bath, if you like, which connects the level 1 to level 3. Okay, and you use, because this pump is, it has some, let's say, temperature T1, and it has a broad band, all kind of frequency. You use a filter which passes only a particular frequency, which couples these two states. And the system is also connected to external contact, which acts as a cold bath, T0, which also coupled these two levels, level 2 and level 3. As a result, what happens, there is a population inversion. Okay, and so this, you can understand this length of this line is proportional to this population. So now you can see that in general, you have the maximum populations in the ground state. But once you pull this population, so there is a populations of the level 2 is now greater than level 1. So there is a population inversion between level 2 and level 1. So as a result, in these two levels, you get this signal, measure and the laser signals in the form of amplifications. So that's how it works. Now you can define an efficiency for this device, which would be the output divided by the input. So what does that mean? There is an energy conservation. So that means for each photon that you take from this hot bath with energy h bar nu p, you get an h bar nu s as a signal between level 2 and level 1. And this h bar nu I is the amount of energy that you dumped into the cold bath. Okay, so therefore this efficiency will be just nu s by nu p. So that's your measure efficiency, if you like. Now, how do you relate this to the thermodynamic efficiency? That's the question. And in this paper, if you look at, this paper was actually only two page with these few equations. And that becomes nowadays is a seminal paper in this field. And what they have done is the following. They write this N2 by N1, populations of this level 2 and level 1 is by just ratio of this N2 by N3 times N3 N1. Okay. Now, as I said, that this level N2 and 3 are thermalized with the cold bath. So they use the populations, I mean, this Boltzmann distribution. And similarly, N3 and N1 with this Boltzmann factor. Then you just rewrite this expression in the second line using the energy conservations. That is, nu p is equal to nu s plus nu I. If you use that, then you end up with this equation. Then you find that this factor nu p by nu s is nothing but your inverse of the eta m, measure efficiency. And this is nothing but hot temperature TH minus TC by TH. So that's nothing but the Carnot efficiency. So you have this in the argument of this exponential. Now you know that in order to get this measure and laser amplifications, you need population inversion. That means N2 has to be greater than N1. That means this has to be greater than 1. So what does that imply? That this argument of this exponential has to be greater than 1. And this immediately implies that this eta m is always less than eta c, which is the Carnot efficiency. So you see that the main lessons of this paper, or this message of this paper, is the limiting efficiency of this 3-level measure is that of the Carnot efficiency. Once it approaches the Carnot, I mean, once it is equal to 1, then you don't have population inversion. You don't get any laser or measure signals. Now, so you can understand why this model is so important, because you see, normally this 3-level atoms, I mean, these 3-level systems is acting like a working medium. In classically, the working medium has a continuous spectrum. And this is the first model where they consider the working medium has the discrete energy level. So in that sense, it is the first quantum heat engine. And there is another fundamental difference between this model and the conventional Carnot cycles, because the Carnot cycles that we have studied, it has strokes. Here, you don't see any strokes, right? The working medium is simultaneously coupled to both cold and hot bath. Okay, so am I audible? So
yes, you are audible.
Okay, fine. So my video is on, or I'm not sure. Okay, fine. Okay, so now you see that this is simultaneously coupled. So it means that this, once you have this in quantum domain, it provides, we have the standard stroke cycles. On top of it, also it provides a new type of cycles. Okay, and this is called, in the quantum thermodynamic language, is called the continuous cycles, because it is simultaneously coupled to both the hot and the cold bath. Now, why this is important? Because in quantum settings, it is because in the nanoscales, if you have this kind of devices, it is sometimes it's very difficult to, this decouple the system from one stroke and again recouple to the other bath. So therefore, this might be very complicated. So what people have done, like to realize it would have been much better if the working medium is simultaneously coupled to both the baths. So this is another variant of heat engines. You can, if you like. And the most important part is that even this kind of engines also still abide by the same Carnot efficiency that we are familiar with the stroke cycles. Okay, so with this, but why this paper, although this paper is much earlier, before this recent interest in quantum thermodynamics, but this paper was overlooked for decades and only get very recent, huge interest in recent times. And many of the, several variants have been proposed for both engines and the refrigerators based on this simple model. Okay, now, so this actually started, if you like, this new development of quantum thermodynamics. If you tell me, okay, so this recent development of quantum thermodynamics actually they somehow started around 2003. Okay, so new interest, this emerging field of quantum thermodynamics that we see nowadays, roughly started, if you like, with this paper, with the science paper, where 4 people, Marlan Scully, Suhail Zuberi, G.S. Agarwal, and Herbert Walther, came up with a very nice proposal that it is possible to extract work from a single heat bath using a vanishing quantum coherence. Now, this is very striking because it contradicts the apparent perception of thermodynamics, because it says that it is possible to extract work from a single heat bath under a cyclic process, which is completely violation of the second law of thermodynamics. But this creates a lot of excitement in the field, and in fact, in 2016. Okay, people have experimentally demonstrated really achieved a single atom heat engine within a Paul trap, radio frequency Paul trap, with a single trapping a single calcium ion. And from that, there is a huge rise in interest in this field of quantum thermodynamics, rise of quantum thermodynamics. And in recent times, people have realized various non-trivial quantum bath, for example, quizzed bath to boost the engine performance. So the whole idea of quantum thermodynamics is then, okay, is it possible to use the quantum effects? Because we know that in quantum mechanics, we have a lot of effects like quantum superposition, coherence, entanglement, tunneling, and so on. So is it possible to implement this effect as a resource, extra thermodynamic resource in the conventional thermodynamic engines to boost the performance? So that's the whole idea of this, the interest of this quantum thermodynamic communities. And at the initial phase, okay, initial 10 to 15 years, people have come up with various proposals with this squeezed bath, then quantum superposition to have this quantum heat engine, using quantum coherence to boost the powers, and so on. Now, I would like to take one example of this first paper, okay, just to clarify one thing, that it should not lead to misunderstanding that using quantum mechanics, you can violate the thermodynamics or you can go beyond the Carnot bound. So that's not true. I mean, so there is initially some confusion or misinterpretation. So I would like to clarify this just using this one paper, and then I will generalize the entire idea. Okay. So here is this paper by Marlan Scully and et al. So if you look at that in their abstract, so this is I discussed the Maser model Now it is a micro-measure model, and in their abstract, what they have written is the following. You see that the deep physics behind the second law of thermodynamics is not violated. Nevertheless, the quantum Carnot engine has certain features that are not possible in a classical engine. So you see that they are saying that although we are saying that it is possible to extract work from a single heat bath, it doesn't mean that I am violating second law. Second law is not still violated. Okay, so we need to understand, so what is going on in this model? Okay, so you may look up also this paper. After this paper, so there is a lot of interest to understand and interpret the results from various perspectives, and I have taken these references. This is a very nice review, you may look up, where they have analyzed very beautifully this model further. Now, what happens in a micro measure, we have the measure problem where you have the 3-level systems, and you create a population inversion to get these measure laser amplifications. On the other hand, in a micro measure, you have a cavity, and instead of using the pump, which acts as a hot bath, what you do, you inject a hot atom into this micro measure cavity, and if you inject the hot atoms, which has hot atoms, that means the atoms that you inject is already in their excited states, and if you inject this atoms in their excited states, you still find out through the analysis, you can define a temperature of this hot bath or the hot atom, which is given by this formula H bar omega n bar kb. Okay, where this n bar is obtained from this equation. So this is the equation of state, where P is the radiation pressure, which acts as a working fluid. V is the cavity volume. Omega is the frequency of this cavity. N bar is the average number of photons in the cavity. And from this, you can define a temperature, effective temperature. And based on that, if you calculate, you still obtain that the efficiency is bounded by Carnot. Okay. On the other hand, in this model, what they have done they use quantum coherence. So instead of injecting 2-level atoms, they inject what they call as phasonium fuels. What is the phasonium fuels? It is a 3-level systems where the lower 2 levels are degenerate. Okay, so which supports some amount of coherence, a small amount of coherence. Based on that, if you inject these phasonium fuels, okay, so then you can similarly define. Okay, so I am not doing this entire analysis just to clarify that this apparent misconception which may appear, that you can still define an effective temperature for this phasonium fuel, which will be then now, instead of n bar, it will depends also on the phase of this coherence, and you can define, and you can still define a similar Carnot-like efficiency, which is Tc by Th T5. Okay, now what is the interesting point is that now this phasonium fuel, because it also has a little bit of coherence through this phase phi, it has some temperature. So it is parameterized by two parameters. One is temperature and one is the phase. Now, if you measure temperature, you may see that, okay, and you set, let's say, the temperature Tc and Th here also. You set the apparent temperature of this bath to be equal. So what does that mean? That means you are no longer have 2 baths, right? You have essentially single bath. So in principle, from classical thermodynamics, in principle, you should not able to extract any work, right? But so in principle, then because this phasonium now also have this phase factor, although I mean this apparent temperature, it may look like, okay, you have the same temperature on both the bath. Because of this presence of this phase, this Th phi is effectively higher than the real temperature, hot bath temperature. And this allows you to still extract work from this phasonium fuel or this model. Okay, so that's how you are still avoid by the second law. So what does that mean? That means once you have, this is because this kind of bath, this kind of phasonium fuel does not allow classical mechanics or classical thermodynamics. You don't have. Quantum mechanics only provides this kind of exotic or non-trivial baths. once you introduce this kind of bath, you need to take into account this to maintain the coherence. You also paid a cost, right? So you need to take into account this cost. Okay, cost of energy. If you take into account, you still find that you are still abide by the classical, the laws of thermodynamics. You are not violating anything. Okay. So that's the important clarification. And this is true not only for quantum coherence, this is true for other quantum resources. Like if you have correlations, entanglement everywhere, you have to take into account this extra cost to prepare the system in this coherent superposition or these, if you have this entanglement or so. Okay, so that's the important part we need to keep in mind. Okay, so with this, now I would like to go into, okay, once we have this clarification, so now we would like to understand, go back to the classical thermodynamics, as I promised. In order to go to this quantum domain, first we need to understand what is the basic principle of the classical thermodynamics. And here I summarizes briefly the concept, really basic concepts. So in classical thermodynamics, the central notion is equilibrium, and the central concept is energy, right? And if you have a system, and the state of this equilibrium state of any systems are uniquely characterized by an equation of state. Now, if you take the ideal gas, this is PV is equal to NKT. So that's your equation of state. Now, what do I mean by equation of state? That means, see, this pressure, volume, temperature. So these are experimentally measurable quantity, and they satisfy this equation. So they are related by this. So this is for any systems, you can define some experimental measurable quantity, and as a function of this, this is equal to 0. So that determines the equation of state for the systems. And all these equilibrium state of the system in the thermodynamic parameter space, like this pressure, volume, and temperature for the ideal gas, lie on this surface. Okay, so this surface, and each point on this surface is one such equilibrium states. Okay, and any thermodynamic process, for example, this green curve, which lie on this surface, is essentially describes a reversible process, because it describes a thermodynamic transformation from one equilibrium state to another equilibrium state in between through succession of infinite number of equilibrium states. So you don't leave this space as long as you stay in this space. Your process is reversible, and you have to perform extremely slowly. That's what the quasi-static process that you have studied in classical thermodynamics. As long as you are on this surface, the process is thermodynamically reversible. If any curve is go out of this plane, then you have the irreversible process. Okay. And then you have this first law of thermodynamics, which states that the energy conservations, and you have the heat and work, and heat and work are two different forms of energy. Work has a mechanical analog, okay, which have in the standard form, it is PdV, okay, and this dV is exact differential. The presence of P makes it inexact. But for heat, which is an inexact differential, to find its corresponding exact differential analog was not trivial, because heat does not have any mechanical analog, and it took process to identify what is it. And we nowadays know that is the entropy, and this 1/T is essentially the integrating factor, which makes this inexact differential dq to be an exact differential, which we nowadays call entropy. And that's the famous Clausius inequality. And then there is third law, which says that this delays for any physical and the chemical ideal process, it goes to 0 at t goes to 0. But I will not, in this talk, I will not get into the third law of thermodynamics, because in quantum settings, this third law have some questionable things, like there are some papers where it has been proposed that this third law may violate, and so on. So we will not get into. We'll mostly focus on this first law. Okay, how to define this equilibrium, states in quantum thermodynamic settings, and what kind of definitions we can use for heat and work, so that, and how do we define these various thermodynamic processes so that we can realize whatever thermodynamic cycles we are familiar with, like the Carnot, Otto, or other cycles in quantum thermodynamic settings. So that's the whole purpose of this talk. But I should also mention, if I don't know if I get the time, but once this transformation goes out of this plane, you have this irreversible process takes place. Then you have this entropy production rate of, which is formulated by Prigogine and then later on Onsager. So this entropy production rate can be expressed in terms of this, what is called the force and the flux. But I will not get into except one concept, is that the local equilibrium assumptions. Okay, but I will explain that when it will come to the context. On the other hand, there is this Onsager reciprocity, which says that Lij, this coefficient, kinetic coefficients, there should be any reciprocity relations in linear response regime in absence of any magnetic field. I should also mention here that although classically we say it's thermodynamics, but there is no dynamics, okay, in classical thermodynamics, as correctly said in Callan's book. So Callan's books, the title is Thermodynamics and Thermostatics. Okay, so no dynamics. But on the other hand, from historical ground, if you look at why thermodynamics is in this terminology behind the name thermodynamics, is the following: that the Lord Kelvin, when he proposed this name, is that time it was thought that that thermodynamics essentially studies the flow of heat, and heat is treated as some kind of fluid which flows from hot bath to cold bath. So that means it's the descriptions of some flow. So in that sense, the dynamics is introduced, but you can understand there is no notion of the time here. So therefore, the classical thermodynamics or the reversible thermodynamics that you have studied there is no real dynamics. But you can understand once you have quantum thermodynamics, because quantum mechanics is intrinsically dynamical in nature through Schrodinger equation. So quantum thermodynamics by itself introduces dynamics to thermodynamics. So that means I'm interested in how the system, okay, approaches equilibrium and so. But for the time being, okay, so with this time being, let's not, I mean, I will discuss also how the system approaches equilibrium, I mean the finite time thermodynamics later on. But first, let us discuss in complete analogy what we have seen, like this description of the thermodynamic state in classical setup, and how to translate the same language in the quantum mechanical context. Okay, so that's the whole idea. And this formalism actually developed by, it's much earlier, in 1978 by Herbert Spohn and Leibovich, who both of them got Boltzmann medal, Boltzmann award, and Robert Alinsky. So these are the formalisms that I am going to summarize. Okay, so for that, what you need to understand, when you have to discuss this quantum thermodynamics, you need to understand that any quantum mechanical system is described by a density operator and a Hamiltonian H. Okay, now again, there might be one confusion that may appear. So let me clarify that, because when you conventionally we have thermodynamic systems, it's a large number of particles, n goes to infinity, v goes to infinity. This is how we'd like to understand it. And we said that n goes to infinity, v goes to infinity, but the density n by v is finite. But if you want that, what is the corresponding analogy in quantum thermodynamics, it is not that straightforward, because you can understand when you discuss thermodynamics for quantum systems, you have to deal with these abstract operators, Hamiltonian in some Hilbert space, then density operator, which is again abstract operators. So you have to understand that only in terms of these operators. And what does that mean? How do I define now the equilibrium state in such setups? Okay, in abstract language. Okay, so that's the main point we need to understand. Now, how this equilibrium is established when you have a quantum systems. The equilibrium is established, a quantum system. Now you consider that it is coupled to some external reservoirs, which has a macroscopic reservoirs, which, so in some sense, the entire system is no longer quantum. It's no longer, not, I would not say quantum, I would say it's no longer microscopic or few degrees of freedom, because this reservoir is treated as a macroscopic systems, which has characteristic temperature, equilibrium temperature. And if you allow the system to equilibrate, then it will eventually thermalize with this, external heat bath. Okay, and here, exactly like in the classical thermodynamic sense, the quasi-static approximation is analogous to the ultra-weak coupling. Okay, between the system and the reservoir. So that's the corresponding analogy. So quasi-static process is replaced by an ultra-weak coupling. If there is a strong coupling, many non-trivial things may happen. You have non-Markovianity, so all sorts of crazy things can happen. So also relax that condition. So consider only ultra-weak coupling, so that if you wait enough, the systems eventually reach an equilibrium state in terms of this density operator, which is given by this rho equilibrium. Okay, e to the power minus beta h by z. Now, if you are not familiar with this density operator, but definitely you have studied classical thermodynamics, statistical mechanics. You have studied distribution functions, canonical distributions or canonical ensembles. Think of exactly, it is the quantum equivalent of it. So rho is essentially, rho equilibrium is the F, or the distribution, or the P, whatever you have, the way you have studied, the canonical distributions, which is e to the power minus beta e by z, and z is the partition functions. If you have the classically, you have the discrete energy levels, you just sum over all the energy levels. The same thing in terms of these abstract operators, sum is replaced by the trace. Okay, so that's the definitions of the quantum mechanical partition functions. And again, you can define the free energy, which is exactly like KTLNZ. So now you see that there is one-to-one correspondence. So in some sense, the quantum thermodynamics, as I said, now it introduces dynamics, how it approaches, although I am not considering the time evolutions, I am considering, okay, system reaches equilibrium. First, I will discuss that. But you see, there is now one-to-one correspondence with these quantum statistical mechanics and this quantum thermodynamics. Eventually, you can think of this quantum thermodynamics is nothing but a non-equilibrium statistical mechanics, okay, or the quantum statistical mechanics in some sense. Okay, once you have these definitions of this rho equilibrium of the systems, now you can define the internal energy as the average, quantum statistical average, which will be the trace of rho equilibrium times h. Okay, and you can also define what is known as the von Neumann entropy, which is exactly like the statistical mechanics is the analog of the Gibbs entropy, which is corresponding quantum mechanical thermodynamic entropy, and exactly the correspondence holds. S is equal to E minus F Helmholtz free energy, E minus F by T. Okay, once you have these definitions of this internal energy, now you can think of, write down the first law. Okay, exactly analogous to the classical way. Now you see that small change in dE can be attributed by two ways. One way is that keeping the density fixed. So if you like, if you have, because quantum mechanically your Hamiltonian have discrete energy levels, right? This rho essentially describe the populations of these individual levels. Okay. Now if you like that you keep the populations of the individual level fixed, you only change this Hamiltonian. Okay, so that means you only change the energy spectrum. So that means you are performing work. Okay, sorry. So these ones get reversed. So this part should be what? dW. Okay, dq dh should be work. On the other hand, this first part should be equivalent to dq. Okay, because you are not changing the energy spectrum, but you are changing these populations of these individual levels. So that means you are supplying heat. Okay, so this is the definitions of the heat and work that we are going to use. Okay, and if you see that This also analogous. If you have from this free energy, if you dF, then it's exactly equivalent to this isothermal process. It's dW. This relation TdS also holds for isothermal process. I will show you how to obtain that. But before, just let me complete this slide with this note that all these definitions you need to again keep in mind. This is true if and only if the system is in this Gibbs state given by this rho equilibrium. If the system is not in Gibbs state, okay, then you need to take into account all kinds of. So if the system is a non-Gibbsian state, that means once you have these extra quantum effects in the form of, as I said, this Kali's paper, okay, this quantum coherence, quantum correlations, then traditionally what happens, the entire change in entropy is related to heat. That's how we understand heat is. But once you have these extra quantum effects in the form of coherence, correlations, the entire change of heat is not equivalent to the entropy change. You need to take into account the cost to create this coherence or these quantum effects resources. So you have to subtract some amount dq, and this dq is actually obtained by this df curl f, what is known as in this technical term is the information's energy, free energy, and you have to subtract, because once you have this non-Gibbsian state, then you have all sorts of complicacy. We will not get into that, but we'll mostly discuss this equilibrium setup, which we are familiar, and then relate how to define heat and work, how to define various thermodynamic process. But you can understand, just to make a note, in order to take into account these extra effects, you need to take into account in a proper formalism. If you want to take into account theoretical framework, then you have to take into account this extra cost to prepare such systems. Then you still abide by this laws of thermodynamics. Okay, so with this, let me now come to this, how to define various isothermal, isochoric, adiabatic process that we are familiar with in the conventional thermodynamics description. Okay, as I said that these definitions, well, here, okay, by the way, here this Descartes, I couldn't, because in Keynote does not support, so I couldn't include it all the places, but hopefully you can understand it. So this is the dq and dw, the first law of thermodynamics, and this is the entropy that I mentioned. And now for isothermal process, you can write TdS. Okay, so from here you can multiply Ts, and TdS you can write, so it will be dE minus dF. Du, use this equation. These equations you write, and dF you just write this. Now you can see that it just cancels. dF is equal to dW. Okay, so as I mentioned in the last slide, once you just get rid of this part and you left with this part, and you see that TdS is equal to dQ. And so for isothermal process, as you see that there is the exact analogy between the classical and the quantum. Now, what about this isochoric process? Classical mechanics, classical thermodynamics, isochoric means constant volume. Okay, now what would be the corresponding analog? Now you should think of, okay, this Hamiltonian, as I said, like it's a quantum mechanical systems. Now traditionally the system is, as I said, like in this SSD or this Scoville's model as a measure model, you have the discrete energy level. So most of the cases it is either model, the system is either modeled by harmonic oscillators or spins, which has discrete energy levels. Now you can think of that if you have harmonic oscillators with a particular frequency, okay, now if you expand, that means the frequency decreases, or if you compress, then the frequency increases. So you can think of the frequency of these systems is inversely proportional to the volume of this system. So that's the analogy you can think of. In that way, you can relate that for isochoric process, what in classical mechanics, classical thermodynamics, the constant volume process, in quantum systems, it is replaced by constant frequency process. So if it is a harmonic oscillators, you have n and omega. So this is the isochoric process. That means you do not have any work exchange, and therefore entire change in energy is through the exchange of this heat. Similarly, adiabatic process, we know that in adiabatic process, there is no heat exchange. So that means there is no population exchange. But you should also remember there is a fundamental difference between the classical adiabatic process and the quantum adiabatic process. Classical adiabatic process normally runs very fast so that there is no heat exchange. But quantum adiabatic process, if you run very fast, then there will be a population exchange between the energy, discrete energy levels, which is not allowed, because then you have a heat exchange. So that is not allowed. So quantum adiabatic process must be carried out very slowly. That means quasi-static process you have to carry it out. So that's the fundamental difference between the quantum adiabatic and the classical adiabatic. Again, if you have, once you include that, you have this exact analogy with this one. So once we have this, then we can implement very easily these standard whatever cycles. Okay, so right now I'm discussing the stroke cycles, because as I said, the continuous cycles is little bit complicated. Maybe I will briefly mention at the end. But you can now understand that all these Carnot cycles, exactly the Stirling cycles, this is also involves this isochoric and isothermal process. You can have exact, this is the classical one in this NMOGA. If it is have a harmonic oscillators, you can think of this Hamiltonian in the number state basis. It has these discrete energy levels and this state. If you calculate the average energy, so it is the individual energy levels and the respective populations of this discrete energy levels. So this energy change will be defined by this way. It can be written as, so you can understand this will be the work and this will be the heat. Okay, so in that way you can identify in an n omega plot how these various curves will look like. Interestingly, the Otto cycle is that Otto cycle involves adiabatic process and the isochoric process. As I said, in isochoric process you do not have work exchange, only heat exchange, and adiabatic process you do not have any heat exchange, only work exchange. So you can see in why this Otto cycle is very important, because in these cycles, these heat and work exchange between these individual levels can be differentiated. So it is not mixed up like in the isothermal process, which involves both heat and work. So therefore, this Otto cycle plays a very important role for the realizations at the quantum settings, because in the quantum levels, microscopic levels, it's very difficult to distinguish between this, differentiate between this heat and work component. So in that way, the Otto cycle is the easiest to realize, because it does not mixed up heat and work. So most of the studied or the experimental realization has been with these Otto cycles. Okay, so with this, I think I have a couple of minutes, right? Hello?
Yes, you can take.
Yeah. Okay, so this is kind of the last slide I have. Okay, so just to give a flavor of this finite time. So far you have studied the standard cycles, the reversible cycles, but you know that in equilibrium thermodynamics, you have the Carnot efficiency, but it sets the maximum efficiency bound for all these reversible heat engines, irrespective of the working medium. But it runs through, when you have this Carnot cycle, for example, you recall that heat exchange between this isothermal stroke at a single temperature. But from the common sense, you can understand that heat cannot exchange at a single temperature. You need at least a temperature gradient, right? So something is problematic, although it's an idealized cycle, gives some universal bound. Okay, because so that's the point, because all these idealized cycle, although they sets a maximum efficiency bound, but since there is no time involved in these entire cycles, the power is absolutely zero, identically zero. So this is no use for any practical purposes. So the practical purposes, all the engine cycles operates in finite time. Right now, I am discussing the classical cycles, classical finite time cycles, how to do that. The same thing can be also developed in the quantum settings. That is much more complicated, so I will not get into. But you get an idea, because this is kind of a seminal papers, and most of the engines, the car engine, automobile engines, whatever you see, nuclear power plant, everything works in this Carnot bond, efficiency bound, and which is different from the Carnot. So let me explain a little bit that you have the temperature gradient, and then what happened, that means you assume the system is in some local equilibrium, which is different from the outside global equilibrium, and there is a temperature gradient. So heat exchange between these isothermal and iso strokes. On the adiabatic, it's fast. Okay, so there is no time. Classically, it's very fast process. And now you assume that because of this temperature gradient, heat is exchanged, QH and QC, with these factors, with it requires some amount to exchange the heat, tau H and tau C. This is the time taken to exchange this heat. And then you can define a power once you have the finite time, because you know now this is the amount of work that I am getting, and this is the time taken. And you can define an efficiency. And if you have these systems at the local equilibrium, again, it's reversible completely, but it is not reversible in the global sense. So therefore, it is irreversible. Therefore, so locally it is reversible. Still, it is Carnot bounded. But if you convert this TC/TH in terms of this outside temperature, the surrounding temperature, so you end up with these very nice results. You can look up this derivation, but now it is square root. Okay, so this is how all these practical cycles works. Okay, in whatever we see, and although these efficiency, I should say that this is not universal in the sense of Carnot, because it depends on this conductivity, kappa and time and so on. So it may violate it, but it is most practical bound. Okay, so with this I conclude. I mentions I don't go into this continuous one, because you can see that continuous one requires much more complicated stuff. Which now you can, with that you can disguise these lasers in a formal theoretical language. And then you also have various quantum thermodynamics, there is a fluctuation. So what we have discussed so far, only these average values, but also there is fluctuations in quantum systems, how to take into account that. Now you can also think of, okay, so is it possible to have real quantum signatures in thermodynamic processes? So these are various references. I will not get into that one. If you are interested, you can look up, and these are the various physical platforms where these things has been realized in ion traps, nanomechanical devices, NV centers, photovoltaic systems, various. But if you are interested, there is this ICTS lecture that I have. It's also available in the YouTube. You may look up that, and they are with whom I have written this introductory review. So with this, I conclude. Okay, thank you for your kind attention.
Thank you, Arnab, for a very interesting talk in a new direction. We normally don't hear of this in our quantum chemistry symposiums. So the floor is open for questions.
Yeah, thank you.
Is there a question from any of the participants? You can simply unmute and ask our question.
Yes.
I have one question. Thank you for your talk.
Yes.
Could you please suggest any reference book on non-equilibrium thermodynamics or quantum thermodynamics, non-equilibrium?
Okay. So I would say, like, okay, so you can, as I said, so you can look at this our paper, and there you get all the references. Also, I mean, in the ICTS, I have modified a little bit. If you look at, I mean, so there is one review by Ronnie Kosloff. Okay, all these references you will get it in the, if you look at this ICTS lecture. I mean, okay, so let me give you this one. Yeah, so this is much more broader, a good review which summarizes all these theoretical concepts as well as the experimental platforms. I mean, whatever I couldn't cover in these lectures, this you can look at. There is a book also by Defner, which is the Introduction to Quantum Thermodynamics and Information. But you can also, if you just look at the first chapter, you will get the essence. You may also look at our review. I mean, it's just few pages. You at least whatever I have discussed in this talk, you get in details. That you also can look at. So that's I mean, you will get the much more better references if you look at these ICTS lectures. Okay, so there I have all the references. I have put it in one slides and so.
So you mean Roni Kozlov from Israel, right?
Yes, from Hebrew
Yeah, okay.
University. Yeah. So he has a paper on dynamical formulations of quantum thermodynamics, laws of quantum thermodynamics from 2003. Okay, so that was the kind of the first review on this subject. I guess 2003 or 2010 or so. Yeah. So yeah.
11 o'clock.
Okay. So anything else?
Are there any practical use of non-equilibrium thermodynamics in quantum computation or quantum information? Do you have any examples?
Yeah, nowadays, see, as I said, like, for example, so the language of these quantum informations I didn't get into. In fact, I am not an expert to talk about on quantum information, but these subject, as I said, like, there are several approaches to do quantum thermodynamics. The quantum information people take a very different approaches to derive the laws of thermodynamics from a very fast principle. Okay. On the other hand, the way I discussed is the following, that we know that we have these classical thermodynamic cycles, how to implement that in quantum settings. And this is how these people also realized. If I just show you for a minute, okay. So for example, this is the first quantum heat engine that has been realized in 2016. So, trapping a single calcium ion in trap. Okay, so then there is this nano beam. Okay, so this is purely non-equilibrium systems. You have a vibrating nano beam, it's a cantilever. Then you shine, electromagnetic radiations on that. Then you complete the cycles. And people initially have proposed that it may even go beyond cross-Carnot. And then if you, as I said, if you take into account this extra effect due to this quantum whizzed bath, then again, you abide by the laws of thermodynamics. So these are, again, is kind of summarized. So this is the results that we have derived in this Nature Communication or Nature Communication paper. So if you do that, then so this is the extra energy that is required to take into account all these quantum effects. Otherwise, you may even go above Carnot, even you may go even unphysical. It may even go above 1. So all sorts of crazy thing initially people have proposed, and now it is kind of resolved to sort of understanding. You have also a quantum flywheel where you have these ions, and then you have two kinds of laser lights where you realize the stroke engines. So many ways to realize this has been, I mean, although it is only few experiments has been done in this setup, but it is still going on.
Thank you.
Okay, so thank you, Dr. Ghosh, for a nice talk and introduction. So are there any further questions? Okay, if not, we can leave for lunch, and then we will be back at 3 p.m. to listen to Professor Saurav Pal on quantum chemistry on quantum computers.
Okay.
Thank you.
Thank you so much. Bye.
Okay.